Good morning. Today we're going to be learning about the formation of solutions. But before we get too much farther, I want to make sure we lay down some terminology and some vocabulary so you understand when I'm using some terms that you know what they're talking about. First of all, what is a solution? A solution is a homogeneous mixture that includes a solute dissolved in the solvent. Now, the term homogeneous, remember, means that it is a mixture where you have two separate pure substances that are physically combined together. And it's homogeneous because all of the particles are evenly distributed about. Basically, the solute, which is the part, that gets dissolved in the solution, okay? And the solvent is the thing that does the dissolving. They're all at the atomic level, okay? So that if you're talking about water molecules, for example, and salt, the salt particles would be ions and they would be at the same size as the water molecules. So that every particle of the solute has an opportunity of touching every particle of the solvent, okay? That's what it means by particles are small enough to be mixed at the atomic level, so every particle can touch every other particle. All right, now solvent, as I said, is a substance that dissolves the solute. Most often we're talking about water, okay? And if it is water, then it is an aqueous solution, all right? That's what a little AQ afterwards signifies. So, but other things can be solvents. You can have turpentine, you can have nail polish remover, you can have all sorts of different substances that can be the solvent. It's just water is by far the most common. Now, solutes are the particles that get dissolved. Now, most of the time we think of them as being solid, okay? But in fact, let's go back there. In fact, they can also be liquid or a gas, all right? So yeah, solid like sugar or salt being dissolved in water, boom, that's going to be a solid solute in a water solvent. But you can also dissolve liquids in solvents. For example, you can dissolve paint in paint thinner, all right? Or you can dissolve nail polish in nail polish remover, or, lots of things like that. So liquids, alcohol can be dissolved in water. Also, you have gases that can be dissolved. Think of oxygen being dissolved in water. That's what fish breathe, all right? Or carbon dioxide being dissolved in water. And that's how you get carbonated beverages, sodas, and so forth. All right, so you have lots of different examples here, some of the ones I've already mentioned. You can even have a solid dissolved in another solid. When we did the golden penny activity, we made brass and we actually dissolved zinc into copper and made an alloy of brass. Kind of trip, huh? The air around us, oxygen can be considered dissolved in nitrogen. Since nitrogen is the most common gas in the atmosphere, then it is considered to be the solvent, and then all the other gases can be considered to be dissolved in it. All right, so it's not just a solid and a liquid. All of these can be considered to be solutions, okay? Now, the process of dissolving is often known as dissociation. If the solute is a covalent compound, think sugar, all right, then usually the intermolecular forces are broken and the molecules become separated from each other. So when you take sugar and you dissolve it in water, because sugar is a polar molecule, then you have the ionic, the polar molecules of the water will attach themselves or grab onto the polar molecules of the sugar and pull them away from each other. And because water is polar and sugar is polar, then we say sugar dissolves in water. But they are separated from each other. You still have the overall sugar molecule being held together, okay? They're not actually all the way separated from each other. However, if it is an ionic compound, then those undergo the process of dissociation. where the compound dissolves into individual cations and anions. All right. This is a process where a compound separates into fragments, such as simpler molecules, atoms, or ions. All right. And for example, salt dissolving in water gives you individual salt ions in the form of sodium cations and chloride anions. Now, the process of dissociation is caused by the presence of water. Now, what we have here is a model, kind of like what you see up on the board. This is a three-dimensional model of what a salt ion would look like, or ionic compound. Now, this is called a crystal matrix, and this particular kind is cubic. This is why, by the way, if you ever looked at a grain of salt under a microscope, they look like little cubes. All right. Now, imagine a typical grain of salt would be this, but stretched out like a couple miles in every direction. Now, you would have, sodium ions and chloride ions, or vice versa, or whatever. Now, in order for dissociation to occur with an ionic compound, it's kind of like a two-part process. First of all, the water molecules weaken the ionic bonds. They do this by being attracted and slipping inside the cracks, as it were, between the ions. All right, they physically get in the cracks in between. And then the polar water molecules will completely surround an ion and carry it off into solution. All right, in a process known as hydration. It's kind of like in Wizard of Oz when all the little flying monkeys engulfed poor, the Tin Man or whatever, and carried them off into the air. That's what happens here. All right, the little water molecules will get into the cracks, surround the individual ions because their ionic charge and the polar charge of the water molecules are attracted to each other. And then they completely surround them and just carry them off into solution. Again, when water does this, this is a process known as hydration. All right. Now, another concept we're going to be talking about is one known as solubility. Now, solubility is the maximum amount of a chemical that will dissolve in a given quantity of a solvent at a specified temperature while the solution is in contact with undissolved solute. In other words, a certain volume of water can only hold a certain amount of sugar, for example. All right. And if the maximum amount is very small, all right, then we consider it to be an insoluble solute. For example, if you take a glass of water and you throw a rock in there, any old rock. Now, believe it or not, some of the rock does in fact dissolve away. Not enough to be noticeable, and therefore we consider that rock to be insoluble. Now, if the maximum is a high maximum, relatively large, then we consider it to be soluble. But nothing is 100% insoluble or 100% soluble. It's all a matter of degrees. Now, when I was small, okay, I used to enjoy watching cartoons on Saturday mornings. And I would wake up before the rest of my family, and I would crawl in there, and I would get some cereal and milk and a TV tray, and I'd just sit there for 5-6 hours watching cartoons. Now, my mom caught on to the fact that if I had too much sugar, I got a little hyperactive and I was hard to control the rest of the day. So she started buying me healthy cereals. Instead of Captain Crunch, I got, Cheerios and grape nuts and things like that. Well, what she didn't know is that I knew where the sugar bowl was. And I knew how to get a chair and move it over to the cupboard and climb on up and get the sugar bowl down. And so I would sit there and I would make a bowl of cereal, and I would just constantly put more sugar in to my bowl of cereal. And my favorite was Cheerios. But the problem with Cheerios is they got a hole. So when you sprinkle sugar on it, some of the sugar goes down the hole and it goes into the milk and gets dissolved by the milk. Well, I'd be sitting there watching TV and adding more and more sugar on. And when I got to the bottom, I added so much sugar that at the bottom of the milk, there was like some sugary sludge at the bottom, okay? Where it was undissolved sugar that was at the bottom of the bowl of milk. Unbeknownst to me, by the way, that was my favorite part, and to sit there and just, start freaking out because it was just too much sugar, but it was awesome. But anyways, I had inadvertently discovered a chemical process known as a saturated solution. A saturated solution is one that, like that milk, contains as much solute as will dissolve at a specified temperature. Okay, so at that temperature, you can tell that it's a saturated solution when you actually have undissolved solid at the bottom. Now, anything short of that is considered an unsaturated solution. It's a solution that contains less solute than the maximum possible at a specified temperature. Okay, now you may have noticed that it always says at a specified temperature. Well, there is a special type of solution known as a supersaturated solution. And this actually contains more dissolved solid than a saturated solution at that temperature should be able to. All right. Now, hopefully, as you know, hot beverages can dissolve more than cold beverages. That's the big thing. If you increase temperature, all right, due to increasing temperature increases solubility. So the hotter the temperature, the more sugar you can dissolve. Now, one of my favorite things is Southern sweet tea. I love Southern sweet tea. Now, it's iced tea, right? But it is really, really sweet. And the way that they make it is as a supersaturated solution. Basically, they make hot tea, right? Or they make it in the sun and it warms it up. And while it is still warm, they put lots of sugar in. And then as it cools off, the sugar stays in solution. Now, if you just try to take some iced tea and put sugar in, you can get some of it to dissolve, but a lot of it will stay at the bottom and it's really hard to dissolve it. So you dissolve it when it's hot and then cool it off. You've made a supersaturated solution. And you can actually put a lot of sugar in or a lot of solute, and you can make a really, really supersaturated solution. So examples are like honey syrup, okay? Now, the problem is it can be unstable. Adding just a single crystal can cause it to precipitate. In other words, to come out of solution and crystallize. All right. Now, to me, this happens sometimes with my with my honey. All right. If sometimes the honey gets warm and then like a little crystal might form. And then when it cools off, that crystal gives like a place for new crystals, sugar crystals to form. And then boom, pretty soon the entire honey is like all crystallized. And you can make it uncrystallized by heating it back up again. But that's what's going on with that. All right. So that's an unstable, and that's a supersaturated solution. Now, the next thing I want to talk to you guys about are the different factors that affect solubility. Now, first of all, we're going to look at solids dissolving in liquids. Think salt or sugar dissolving in water. Now, increasing the temperature, as I mentioned before, increases both the solubility and it also increases how fast the salt will dissolve, how fast the solute will dissolve. All right. So, you take hot water or cold water, you throw sugar into both, the sugar is going to dissolve faster in the hot water than it will in the cold water. It also will dissolve more of it. Something else is increasing agitation. All right. If you want sugar to dissolve in like iced tea or something, you sit there and you stir it. That's what agitation means. Agitation is the, it's like the scientific way of saying stirring or shaking. All right. So that speeds up the dissolving process. Also increasing the solute's surface area. All right. Think about this. Imagine you get a piece of hard candy, like a butterscotch or a Jolly Rancher or something like that. A mint, something. Now, if you put it in your mouth and you just, let it sit in there and you suck on just the hard candy in one big piece, it'll last a lot longer than if you put the same piece of candy in your mouth and chew it up. See, when you chew it up, you increase the surface area. The more surface area means the more area for the water molecules to come and attack and dissolve away the sugar or salt or whatever. I mean, if you look at it, if this is the size of a particle, I have this much surface area, water can dissolve it at a certain rate. But if I take this same crystal and break it in half, well, I've just increased a whole bunch, by like a third how much more surface area it has, and it'll dissolve that much faster. So increasing a solute's surface area speeds up the dissolving process. Now, another set of factors I want to look at are when you have gases dissolved in liquids. All right. Now, the classic example of this is when you have carbon dioxide dissolved in water and you have soda, like a Sprite or a Coke or something. All right. And here, the factors are different. It's different than with the solid. First of all, increasing temperature with a gas decreases its solubility. It's the opposite than it was with a solid. All right, think about it. When you drink a soda, if it tastes normal or whatever, then we say it tastes crisp or whatever. But if you let it sit out for a long time or whatever, you know that it goes flat. All right. So think about it. If you have what tastes flatter, a Coke or a warm Coke? The warm Coke, right? That's because you increase the temperature and more of the gas has left the solution and it's flatter, all right? Not as much gas dissolved. Also, increasing agitation. In other words, stirring or shaking will decrease the solubility. All right? You know this. If you take a soda and you shake it up and then you open it up in your friend's face, it all comes out. That's all of the gas coming out at once because you've decreased the solubility, all right? So stirring or shaking decreases the solubility of a gas in a liquid. Now, increasing a gas's partial pressure over the liquid increases the solubility. Think about a soda bottle, all right, like Sprite. If you notice, when you have a Sprite bottle, at the top, there's a space that is not filled all the way up with Sprite. Now, when I was young and stupid, I used to get cranky about that because it was like, man, they're cheating us. Why don't they put soda all the way to the top, right? Well, they need to keep that space in. In that space is some high pressure carbon dioxide. And that high pressure kind of forces the gas to stay in solution. Think about it. If you have an unopened Sprite and you look at it, there's no bubbles, are there? I mean, unless you shake it. But if you just look at it, there's no bubbles. The bubbles only start appearing when you open the bottle, right? You open the bottle, you go, psh, you let out that high pressure at the top, and then all the bubbles can start coming out. You've just decreased the solubility by decreasing the CO2's partial pressure over the liquid. Kind of crazy, huh? And then finally, increasing nucleation sites. All right. This is, I don't know if you've ever seen, and I think, I'm going to put in a little video, I think here, of, I'll have available a little video so you guys can click on it, of a Mentos in Diet Coke. I don't know if you've ever seen this demonstration or not, but you put Mentos in Diet Coke and it just causes the Coke to spew up like a geyser. It's really cool. Now, the reason why it does that is because the Mentos actually has, if you're looking at Mentos, it looks like, all smooth and everything. But if you look at it with a microscope, it has little tiny pits and divots, like a little golf ball has like these little divots in it. And when it goes inside a soda, the little bubbles can attach to those little divots. And those little bubbles, it's a lot easier for a bubble that's already there to get bigger than for a new bubble to form. So if you're like CO2 floating about in water, it's hard to form a bubble. You need to, you do that rather slowly. But if you have a bubble already there, then all the CO2 can rush in, form a big bubble, And that's what you actually can see with your eyes. And then it comes up and so forth. So that's what happens. It's that nucleation site. It's like a little nucleus that allows the bubbles to grow rapidly. And that decreases a gas's solubility. Again, Mentos in Diet Coke. All right. Now, next things are liquids dissolved in other liquids. Now, this is kind of a weird concept, but do you ever notice how certain paints, you can wash your brushes with water, but other type of paint, like nail polish, whatever, you can't wash it off with water. Instead, you need to wash it off with paint thinner or turpentine or nail polish remover, something like that. And that brings up this concept known as like dissolves like. All right. Now, when two liquids will dissolve in each other, we say that they are miscible. Miscible. It indicates liquids that will dissolve in each other. In other words, they will mix. And if they don't dissolve in each other, think oil and water, all right, then they are immiscible. They don't mix. And it's all about polarity, molecular polarity. If you have two non-polar molecules, like oil and turpentine, those are non-polar. Therefore, they will mix together. However, if you have, oil and water, water is polar, oil is non-polar, they won't mix. They repel each other. All right? So two polar molecules are miscible, or two separate non-polar molecules are miscible. All right? But if you mix them where you have a polar and a non-polar, they are immiscible. And this is kind of important, obviously for cleaning paintbrushes and stuff. But it also comes into effect when you have vitamins. Now, this is a real quick aside. Vitamins are very, very important for your body. Your body produces usually enough that it needs, except for the vitamins that you need in the food that you eat, because your body can't produce them. And they help the different chemical reactions in your body occur. Now, most vitamins are water soluble, which means if you take a lot of those vitamins and they just get flushed out in your system when you drink water. But other vitamins, like vitamins A, D, E, and K, those are non-polar vitamins. Therefore, when you eat those, they don't get flushed out in your system. Instead, they go and they get stored with your fat, like in your liver and so forth. And you can actually get too much of those vitamins. All right. And it is in fact possible to overdose on them and to cause severe liver damage. So you want to be very careful. One of the things that has some of these vitamins are like diet pills, pills that theoretically take away your appetite. You got to be very careful because people have died taking too many diet pills at once because they have these vitamins. Now, one way to keep in, remember which ones you can overdose on. If you notice, these four, A, D, E, K, they kind of spell addict. And who overdoses on drugs but drug addicts? Okay, so something to help you out to try and remember that A, D, E, and K are non-polar and you can overdose on them. All right. So again, talking about miscible, right here, for example, you have alcohol. This is ethyl alcohol or ethanol. And this is what is this is like drinking alcohol, like in beer and wine and so forth. Now, ethanol is miscible with water because both are polar molecules. All right. You can imagine water looks a lot like this little part right here, right? And so since this is polar, a polar bond, this is negative, this is positive, the water molecules have a place where they can attach onto, all right? Like this. And you end up with the hydrogen bond and so forth. Now, immiscible is like, as I said, oil and water. Oil is nothing but hydrocarbon chains. And so there's no polar part for the water to attach onto. So they do not mix. They are immiscible. All right. So Water-water hydrogen bonds keep the water from mixing with the nonpolar molecules. The water is attached to itself and won't even want to go inside there. That's why if you put like water on a greasy pan, the water beads up and like holding on together, won't even mix with the oil at all. It's repelled by the oil. All right. And that comes to the end of this little lecture on the forming of solutions. All right. I hope that you found this informative. If you have any questions, please ask me during tutorial. Bye-bye.